One of the biggest mistakes students make in organic chemistry is forgetting carbocation rearrangements. A student will learn the mechanism correctly, draw the carbocation intermediate correctly, and then completely miss the rearrangement step. And unfortunately, professors love testing this. The good news is that carbocation rearrangements are actually very systematic. If you can recognize when a carbocation forms, you can train yourself to automatically check for rearrangements every single time. That is the key habit. Anytime you form a carbocation intermediate, stop and ask yourself one question. Can this carbocation become more stable? If the answer is yes, a rearrangement will usually occur. So first, let's discuss why rearrangements happen. Carbocations are electron deficient. This means that carbocations do not have a full octet. Carbocations have 3 bonds, and based on octet rules, 1 bond is equal to sharing 2 electrons, so carbocations have 6 electrons. Lacking an octet, that would be 8 electrons. The positively charged carbon only has 6 electrons around it, which makes it very unstable and highly reactive. Organic molecules naturally try to move toward more stable carbocations whenever possible. In general, more substituted carbocations are more stable. Tertiary carbocations are more stable than secondary carbocations. Secondary carbocations are more stable than primary carbocations. Primary carbocations are more stable than methyl carbocations, and vinylic carbocations are the worst. Benzylic carbocations are the most stable of all. And allylic carbocations are more stable than tertiary. A benzylic carbocation is a carbon with a positive charge next to the benzene ring. An allylic carbocation is a carbon with a positive charge next to a double bond. A tertiary carbocation is a carbon with a positive charge bonded to 3 other carbons. A secondary carbocation is a carbon with a positive charge bonded to 2 other carbons. A primary carbocation is a carbon with a positive charge bonded to 1 other carbon. A methyl carbocation is a CH3 group with a positive charge. A vinylic carbocation is a carbon with a positive charge that is directly connected to a double bond. So whenever a less stable carbocation can rearrange into a more stable one, the rearrangement usually happens immediately. We can only rearrange if the more stable carbon is right next to the carbocation, so they have to be sharing a bond. There are 2 major rearrangements students see most often: hydride shifts and methyl shifts. A hydride shift happens when a hydrogen atom with its bonding electrons moves to the carbocation. A methyl shift happens when a methyl group moves with its bonding electrons to the carbocation. There are specific rules you can memorize, but the easiest will be: if the more substituted carbon next to the carbocation has any hydrogens, a hydride shift will occur. If the more substituted carbon next to the carbocation does not have any hydrogens, then a methyl will move and a methyl shift will occur. If the carbocation is next to a 4-membered ring or a ring with a lot of strain, then a ring expansion will occur, where the ring will get larger by 1 carbon. 6-membered rings are the most stable, because each bond exhibits the ideal 109.5-degree bond angles with no ring strain. In all cases, the positive charge moves to a new carbon. Now here is the most important habit for mechanisms. The second you draw a carbocation, immediately check the adjacent carbons. Ask yourself 2 questions. Are either of these carbons more substituted than my carbocation I have now? Or can I make a less strained or larger ring? If yes, a rearrangement is likely. Now let's go through several examples. Example 1. Hydride shifts. 3-methyl-1-butene reacting with HBr. The double bond attacks the hydrogen from HBr and the bromide ion leaves. The carbocation is created on the more substituted carbon of the double bond. After protonation of the alkene, a secondary carbocation forms. Now we can look at the carbons next to our carbocation. 1 neighboring carbon is primary, but the other neighboring carbon is tertiary. The carbocation we have now is secondary. We have a more substituted carbon directly adjacent to our carbocation. The tertiary carbon has a hydrogen attached to it, so a hydride shift can occur. A hydride, which is a hydrogen atom with its bonding pair of electrons, shifts from the tertiary carbon onto the carbocation center. As the hydride moves, the positive charge relocates to the carbon that lost the hydride. This creates a new tertiary carbocation. Remember, Carbocation rearrangements occur because the molecule is trying to form the most stable carbocation possible. A tertiary carbocation is more stable than a secondary carbocation. Now that the more stable carbocation has formed, the bromide ion attacks the positively charged carbon. This produces the rearranged alkyl bromide product. Whenever a carbocation forms, always check the carbons directly next to it for possible hydride shifts that would create a more substituted carbocation. Example 2. Methyl shift. 3,3-dimethyl-2-butanol reacting with concentrated sulfuric acid and heat. After protonation of the alcohol and loss of water, a secondary carbocation forms. Now we can look at the carbons next to our carbocation. The carbon to the left is primary, and the carbon to the right is quaternary. A quaternary carbon is a carbon that is bonded to 4 other carbons. The carbocation we have now is secondary. We have a more substituted carbon next to our carbocation. The more substituted carbon does not have any hydrogens, so a methyl shift will occur. A methyl group shifts to create a tertiary carbocation. The positive charge relocates to the more substituted carbon. Then elimination can occur to create the alkene. Example 3. Ring expansion followed by a hydride shift. 1-cyclobutyl-1-butanol reacting with HBr. First, the alcohol oxygen is protonated by HBr, converting the poor leaving group into a good leaving group, water. Water then leaves, forming a carbocation on the carbon attached to the cyclobutane ring. Now we should examine the carbocation. It is located adjacent to a 4-membered ring. 4-membered rings contain significant ring strain because their bond angles are forced away from the ideal tetrahedral angle. The molecule can lower its energy by undergoing a ring expansion. One of the carbon-carbon bonds in the cyclobutane ring shifts toward the carbocation center. As that bond moves, the positive charge relocates and the 4-membered ring expands into a 5-membered ring. This produces a cyclopentane ring, which has much less ring strain and is therefore more stable. However, we are not finished yet. Whenever a carbocation forms, we should continue checking for possible rearrangements. After the ring expansion, the carbocation is still not the most stable carbocation available. Looking at the carbons adjacent to the new carbocation, we find a tertiary carbon containing a hydrogen atom. A hydride shift occurs from the tertiary carbon to the carbocation center. As the hydride moves, the positive charge relocates to the carbon that lost the hydride. This creates a tertiary carbocation, which is more stable than the carbocation formed immediately after the ring expansion. Now the molecule has achieved both a less strained ring and a more stable carbocation. Finally, the bromide ion attacks the tertiary carbocation. The result is a rearranged alkyl bromide that has undergone both a ring expansion and a hydride shift. When working with ring systems, remember that multiple rearrangements can occur. A ring expansion may happen first to relieve ring strain, followed by a hydride or methyl shift to create the most stable carbocation possible. Example 4. Hydride shift during alkene hydration. 4-methyl-2-pentene reacting with water and dilute sulfuric acid. Sulfuric acid and water create the hydronium ion used in the mechanism. The double bond attacks a hydrogen ion. Protonation of the alkene initially forms a secondary carbocation. Now we can look at the carbons next to our carbocation. One neighboring carbon is secondary, but the carbon on the other side is tertiary because it is attached to 3 other carbons. The carbocation we have now is secondary. We have a more substituted carbon adjacent to our carbocation. The tertiary carbon contains a hydrogen that can move. A hydride shift occurs from the tertiary carbon to the carbocation center. As the hydride moves, the positive charge relocates to the carbon that lost the hydride. This creates a tertiary carbocation. The rearrangement occurs because tertiary carbocations are more stable than secondary carbocations. Now that the more stable carbocation has formed, a water molecule acts as a nucleophile and attacks the positively charged carbon. This forms an oxonium ion intermediate, which is an oxygen atom bonded to 3 atoms and carrying a positive charge. Another water molecule removes the extra proton from oxygen. After deprotonation, a neutral alcohol is formed. The final product is a rearranged alcohol because the hydride shift occurred before water attacked the carbocation. When solving hydration reactions, remember that water does not necessarily attack the first carbocation that forms. Always check for possible carbocation rearrangements before drawing the final alcohol product. Example 5. Methyl shift in a ring. 3,3-dimethylcyclopentene reacting with HBr. The double bond attacks the hydrogen from HBr and the bromide leaves. Now we can look at the carbons next to our carbocation. One neighboring carbon is secondary, but the carbon bearing the methyl group is quaternary because it is attached to 4 other carbons. The carbocation we have now is secondary. We have a more substituted carbon next to our carbocation. A hydride shift cannot occur because the quaternary carbon does not have a hydrogen available to move. Instead, a methyl shift occurs. The methyl group moves from the tertiary carbon to the carbocation center. This creates a new tertiary carbocation and relocates the positive charge onto the more substituted carbon. The bromide ion then attacks the carbocation. The final product contains bromine attached to the tertiary carbon formed after the methyl shift. Whenever you form a carbocation in a ring, always check the neighboring carbons for a possible rearrangement. If a methyl shift creates a more stable carbocation, the rearrangement will occur before the nucleophile attacks. Now let's discuss the situations where rearrangements commonly appear. You should always check for rearrangements in reactions involving carbocations. This includes SN1 reactions, E1 reactions, alkene hydration, hydrohalogenation reactions with HBr or HCl, and alcohol dehydration. If a carbocation appears in the mechanism, you should immediately pause and check adjacent carbons. Now let's discuss common mistakes. Mistake number 1. Checking every carbon in the molecule. Students sometimes search the entire structure looking for a possible shift. Only look at the carbons directly adjacent to the carbocation. Hydride shifts and methyl shifts can only occur from neighboring carbons. If the carbon is not directly attached to the carbocation, it cannot shift in a single step. Mistake number 2. Forgetting to check for hydrogens before drawing a hydride shift. A hydride shift requires a hydrogen on the neighboring carbon. If there is no hydrogen available, a hydride shift cannot occur. Always check whether the neighboring carbon has a hydrogen before drawing the rearrangement. Mistake number 3. Stopping after the first rearrangement. Sometimes one rearrangement creates a new carbocation that can rearrange again. After every shift, reevaluate the new carbocation. Ask yourself whether an even more stable carbocation can still be formed. Mistake number 4. Ignoring the degree of the carbocation after a shift. Students often perform a hydride or methyl shift without checking whether the new carbocation is actually more stable. After the rearrangement, determine whether the carbocation is primary, secondary, or tertiary. If stability does not increase, the rearrangement is unlikely to occur. Mistake number 5. Letting the nucleophile attack too early. Once a carbocation forms, students often immediately draw bromide, water, or another nucleophile attacking. Before any nucleophile attacks, check for possible rearrangements. The carbocation will usually rearrange first if a more stable carbocation can be formed. So if you remember one thing from this video, remember this. Every time you form a carbocation, stop and check the adjacent carbons. Can you make a more substituted carbocation? Can you reduce ring strain? If the answer is yes, a rearrangement will probably occur. And once you build that habit, organic chemistry mechanisms become much easier to predict.